Hello everyone, I welcome you all to the lecture series of Haloalkanes and Haloarenes. This is lecture number 3. In the previous lecture, we have discussed about chemical properties and nucleophilic substitution reaction. What you are observing on the board, this we have discussed in the previous lecture. So let's start. Let's just revise once have a look at what a nucleophilic substitution reaction is. So nucleophilic substitution reaction is a chemical reaction in which nucleophile is substituting a living group in some organic compound. The nucleophile can be negatively charged, neutral. So there are different nucleophilic substitution reaction we have studied. Reaction with aqueous KOH, this yields alcohol. Reaction with sodium alkoxide, that is Williamson ether synthesis. In this reaction, the point to remember is that the halide must be primary. It must not be secondary or tertiary, because if it's secondary or tertiary, elimination takes place. And even if it's vinyl or phenyl, then partial double bond character is there, reaction will not occur, hence it must be primary, allyl or benzyl. The R dash O negative Na positive must be primary, secondary or tertiary. This can be allyl, vinyl, phenyl or benzyl. Okay, this can be all these. So R dash O negative Na positive alkoxide ion, sodium alkoxide ion. It can be secondary, primary, secondary or tertiary, but R must be primary always. Secondary or tertiary, it must not be. Then reaction with KSH, this is similar to reaction with KOH. Next to this is reaction with R dash S negative Na positive. This is also similar to R dash O negative Na positive. Next to this is R dash C triple bond C negative Na positive, RCl. This will form R C triple bond C R dash plus NaCl. Next is reaction with KCN. This will form RCN plus KCl. KCN is having ionic bond. Next to this is reaction with AgCN. AgCN is having covalent bond. So what happens here is nitrogen is something which attacks the R, and here the carbon atom is attacking on R group. Okay, so cyanide is formed while reaction with KCN and AgCN. R and triple bond C, that is isocyanide, is formed. Then reaction with KNO2. RCl reacts with KNO2 to form RONO, that is isonitro or nitroso alkane. AgNO2, then nitroalkane is formed. Next is Corey-House synthesis, reaction with R2CuLi, generally used to prepare unsymmetrical hydrocarbons. Next to this is 10th reaction we have studied, is reaction with silver salt of carboxylic acids. In this ester are formed. Next is Finkelstein reaction. Next to this is Schwarz reaction, and next to this is Hoffman's exhaustive ammonolysis, reaction of ammonia with haloalkane followed by heating yields primary amine plus HCl. If it is further reacted with haloalkane, then it will yield secondary amine, tertiary amine, and further quaternary ammonium salt. If RCl is in excess, then only these steps will occur, and the reaction will be known as Hoffman's exhaustive ammonolysis. Suppose if RCl is not in excess, ammonia is in excess, then what is formed is RNH2 plus HCl. Next is reaction with Na in the presence of dry ether, that will form RR, and reaction with magnesium in the presence of dry ether, that will form Grignard's reagent. So these all are different nucleophilic substitution reaction we have studied in our previous lecture. Let's now begin our lecture with SN2, substitution nucleophilic bimolecular reaction. This is a single step reaction. So there is a substrate and nucleophile. Nucleophile will attack on this carbon from the other side to which chlorine is present, to which living group is present. So it will form a transition state in which living group is leaving the compound while the nucleophile is getting attached to the substrate. After this transition state, what is formed is the product, that is alcohol, butane 2-ol is formed. So what we have taken is the chiral carbon. Just to explain the optical activity of the chemical reaction. So it's just like inversion of the configuration, similar to if umbrella is like this and a strong wind comes and it will become like this. Okay, so that's inversion of configuration. So it is similar to this, that on one side chlorine was attached, OH came, and it's just the configuration of molecule gets inverted. Okay, so that's something known as inversion taking place in the SN2 reaction. Here we have taken the chiral carbon just to explain optical activity of the reaction. So if D form is there, it will get converted into L form. If L form is there, it will get converted into D form. Dextra rotatory will get converted into lever rotatory, and lever rotatory will get converted into dextra rotatory. The optical activity of the compound, either it's dextra rotatory or lever rotatory, it can be predicted by merely looking at the structure of the molecule. It can only be predicted experimentally. So whatever the initial configuration of molecule is, it will get inverted, and this is known as inversion of configuration. Okay, so that's something which is known as inversion. Now, SN2 regarding SN2 reaction, first thing we have to mention is the rate of reaction is inversely proportional to steric hindrance. Okay, since the reaction is taking place in a single step, so from one side is nucleophile is attacking, and from another side the leaving group is leaving. So the lesser the hindrance will be, more will be the tendency for nucleophile to attack. Second is, what we need here is the strong nucleophile. So because of this, primary will show maximum reactivity for SN2 reaction, secondary then tertiary. So if the halide is primary, then there are maximum chances for SN2 reaction to occur, that the reaction will proceed by SN2 mechanism. If a strong nucleophile is there, there are less chances for the formation of carbocation, and hence the reaction will occur by SN2 mechanism. One more thing is the rate law equation for the chemical reaction. Rate of the reaction is equal to K, the concentration of substrate, that is RCl, and concentration of nucleophile. So the rate of the reaction is dependent on both substrate as well as the nucleophile. Third, rate of reaction is dependent on concentration of both substrate, that is reactant, that is haloalkane, as well as the nucleophile. Okay, what we can write here RCl and Nu, or you can write substrate also, substrate and nucleophile. Okay, so rate of reaction is dependent on concentration of both RCl and nucleophile, haloalkane and nucleophile. On both of will be participating in deciding the rate of the reaction, both concentration. Next to this is The tendency of leaving group to leave will also decide the rate of the reaction. Rate of reaction is directly proportional to tendency of leaving group to leave. So Ri will be maximum reactive here, then Rbr, then Rcl, then Rf. So this reactivity order will be same for SN1 and SN2 reaction. That is because uh, it's dependent on bond length, and Ri is having maximum bond length, so the bond is easier to break, and hence I negative is a better leaving group than Br negative, then Cl negative, then F negative. So the rate of the reaction increases with decrease in bond dissociation energy, or lesser is the bond dissociation energy, or easily a leaving group can leave, more is the rate of a chemical reaction. Fifth is inversion of configuration is taking place here. Inversion of configuration. Okay, so that's all about the SN2 reaction. Now let's move ahead for SN1 reaction, that is substitution, nucleophilic, unimolecular reaction, that is SN1. So Rx here forms R positive plus X negative in the first step. So step 1 for the chemical reaction is the formation of carbocation. Formation of carbocation. This is the step 1 for the chemical reaction. Next is step 2. Step 2 is the attack of nucleophile. I would like to take a chiral carbon compound here so that I can explain the optical activity of the chemical reaction. So I am taking here 2-chlorobutane. So it will be reacted with, say, any nucleophile, and this will form nucleophile will not participate in first step. Sorry. So nucleophile will not participate in first step. It will form carbocation plus chloride ion. So this is rate determining step of the chemical reaction. Next is step number 2, that is attack of nucleophile. Attack of nucleophile will be on the carbocation form. So in this carbocation, the nucleophile can attack from both the sides. So there is 50% probability for nucleophile to attack from both the different sides. Hence what this forms is, So in this chemical reaction, a optically active compound is getting converted into a optically inactive racemic mixture having equimolar concentration of D and L form. So what's happening here is the racemization. So first point I would like to mention here is this is a two-step reaction. Okay, and the step one, that is formation of carbocation, that is the slowest step of the reaction, which is rate determining step. Since formation of carbocation has to be take place here, the reaction will be familiar in polar protic solvents. Polar protic solvents means these solvents like H2O, acetic acid, methanol. So these are the polar protic solvents. So these will favor the SN1 reaction because these will help in the polarization of molecule, and hence these they will participate in the formation of carbocation. Protic means which can donate H plus ion. Polar means simply which is polar. Electronegativity difference is there. Third one is the rate of the reaction is directly proportional to stability of carbocation. Since the rate of reaction is directly proportional to stability of carbocation, so tertiary carbon will be most stable, then secondary, and then primary. So reaction will be most familiar for the tertiary carbon, then for secondary, and then for primary. Alkyl halide. Definitely this order we are writing here for the alkyl halides. For tertiary alkyl halides, the reaction will be most familiar because tertiary carbocation is formed here, then secondary, and then primary. Fourth one is the tendency of leaving group to leave. Rate of the reaction is directly proportional to tendency of leaving group to leave. It is similar to SN2 mechanism. Ri will be most reactive, then RBr, then RCl, then RF. Fifth one, we can mention here is mm, the rate of reaction is only dependent on concentration of substrate. Rate of reaction will be equal to, it's independent of the concentration of nucleophile because rate determining step is not having nucleophile in it, since the rate of the reaction is dependent on the concentration of substrate only. And it is independent of the concentration of nucleophile. So this is a first order reaction. More points we can mention here is the sixth one we can mention here. Racemic mixture is formed here. that is equimolar mixture of D and L form. So equimolar mixture of D and L form is formed here in the SN1 reaction. So that's all about SN1 reaction. If D form is there initially, then it will get converted into D form plus L form, and both will be concentration will be 50% and 50%. And if it's L form initially, then it will get converted into a mixture having D form plus L form 50-50%. Now the net rotation of plane polarized light with the help of this mixture is zero. So this mixture is basically optically inactive in nature. Even though molecule is a chiral only here also, but still it is optically inactive because the D and L form are present in equimolar amount, and this is optically active mixture. So if the reaction proceeds by SN1 mechanism, the solution loses its optical activity, will not rotate the plane polarized light any further. That's about SN1 reaction. Okay, so let's end our lecture here only. So this was all about SN2 reaction and SN1 reaction. Thanks for watching the video. Have a good day. Bye bye.